Good afternoon, everyone. Thank you for coming to join us at the Citrus Research Exchange this afternoon. I'm Camille Crittenden. I direct the Data and Democracy Initiative here at Citrus. A lot of what Data and Democracy tries to encourage is increasing social networks, especially for people who want to provide more information about or receive more information about decisions on a range of topics, social, economic, political decisions. So we're really delighted to have Chen-Nee Chuah here this afternoon to talk about some of her research on those social networks. I'd like to also welcome our web viewers. We have people also viewing remotely at our other campuses. Citrus campuses include not just Berkeley, but also Davis, Santa Cruz, and Merced. And I know that a number of our viewers will also be watching remotely from their homes or offices as well. So we're delighted to have you join us. If you'd like to participate during the question and answer session, we welcome your tweets. And there's a Twitter hashtag on the website that you can follow if you'd like to submit a question that way. We've had some remote participation in the last few talks, which has been really great. Quickly, just want to announce that there will be no I4 Energy talk this Friday. Often there is a talk from the Energy Group on Friday afternoons, but before the holiday weekend, we're not having a talk this Friday. I'd like to introduce our featured speaker this afternoon. Chen-Nee Chuah is a professor in the Electrical and Computer Engineering Department at the University of California, Davis. She received her Ph.D. in Electrical Engineering and Computer Sciences here at UC Berkeley. Her research interests are in the general area of computer networks and wireless mobile computing with emphasis on internet measurements, network management, anomaly detection, and online social networks. Please join me in welcoming Professor Chuah. Thank you. Hi. Today I want to talk to you about actually measuring and modeling user activity graphs that basically represent user interactions on OSN-based applications. So I guess I don't have to kind of talk about how popular online social networks are these days. I mean, Facebook today have more than 1 billion monthly active users as of December 2012, and 680 million monthly active users using mobile products. And I guess this number is just going to increase even more. And what is interesting is actually in a survey in 2010, it shows that online social network platforms actually account for 22% of all time spent online. All right? And so what makes online social networks or user interactions on online social networks so interesting? I mean, for a networking researcher like myself. Now, if you compare online social networks with traditional social networks, I mean, obviously there have been a lot of literature on modeling and trying to understanding traditional online social networks. Now, some of the differences are, well, traditionally, right, with friendship formation, in order to form friendship, right, it takes some effort, right, in real life for a traditional social network. Here, online, all it takes is just a click, right? So it's low to zero cost to form a link between two nodes. Now, there is almost no friendship boundary. You can make friends with friends around the world. And more importantly, there is very rich interaction features. I mean, you can share a link, a website that you like, a video that you like. You can share pictures. Besides writing on wall posts, you can comment. So it becomes very content and application-centric, right? And one of the more interesting things is, I mean, this whole idea about open development platform, for example, the ones that was launched by Facebook back in 2007, that allowed third-party application developers to develop novel applications and advertise it to the users, and they have a huge user base, underlying user base, to start using the applications. So as of today, there are 42 million pages that are shared on Facebook. There are 9 million applications and growing. Now, as a result of that, social gaming, for example, on Facebook, has become a multi-billion industry, right? So how many of you have played Farmville? No? Any other Facebook applications or gaming that you use? Not this crowd? Yes? All right, so obviously the next wave of growth that everyone is kind of looking for is mobile social, all right? All right, so in terms of friendship and activities in online social networks. There have been a lot of studies in recent years on trying to measure and model friendship graphs. So, for example, social cascades in Flickr, where you share photos, Facebook social graphs, as well as, they have a study that showed that actually you have 4 degrees of separation with the online friendship instead of 6 degrees of separation. Now, bear in mind, though, when you talk about friendship graphs, typically the graphs are pretty static in the sense that if you have 2 nodes representing 2 users and a link representing a friendship between them, typically that friendship relationship is pretty static. Yes, you do defriend friends on Facebook, but it doesn't happen like daily. Right? It happens once in a while. Now, activity graphs, on the other hand, right, are very dynamic in nature. And the user pairs, the user nodes in that graph comes and go. It's transient. So when it's using the applications actively, the node is active and generating activities. Otherwise, it goes away. Right? So why do we study user activity? Well, from the economical standpoint, the worth of an OSN actually resides in how much activity is drawing, right, from the user, how much time users are spending in this OSN, and not so much of how connected the user base is, right? So, for example, back in February 2012, there was a survey and study that shows that users spend about 3 minutes per month on Google+ versus Facebook, which is like 6-7 hours a month. Okay. Now, again, from a networking researcher's standpoint, at the beginning, I was kind of intrigued, and what piqued my interest about studying user interactions on OSN is that, to me, it's a new kind of workload. Just like how web and peer-to-peer become increasingly important and have some implications on how we design and manage our network. To me at the time, I was curious, how the OSN workloads actually look like. What are the usage characteristics, and how does that have any? Does that have any impact on how we design the underlying architecture or protocols to support that, to make sure that the end-to-end users are happy with the performance? So for the rest of my talk, what I want to focus on is not so much online social graphs per se, not the friendship graph, but their activities. Right? So I'm interested in looking at user activity graphs. It's built upon OSN-based applications, and a node here represents a user, and a directed edge represents an action that user A performs on user B. Now, for me, this is a gateway to study the nature of user dynamics, and this is a dynamic graph because the nodes and edges are transient. And one thing to keep in mind is, unlike friendship, usually a link is reciprocal, right? So your friend A is friend with a B, B is a friend with an A. Here, the UAGs are directed in nature. So, user A can generate an activity, for example, sending a virtual gift to B, but B might not respond. Okay? So the focus of our study is we try to measure and model the evolution of these user activity graphs. Right? So we were particularly interested in understanding what contributed to the growth? How do we? Can we predict when an application or OSN graph, the UAG graph like this, is going to go viral? How does it morph across different stages of the application? So obviously, if you look at the lifespan of an OSN application, there is a ramp-up time when it was first deployed, and then if it became very successful, right? There is a peak activity where the application is mature, attracts a lot of users, and then there is also what we call a post-peak or a fatigue phase where the application starts to lose its popularity. So, there are some implications that we're interested in studying associated with the UAGs. For example, can we predict viral growth, right? Can we predict the size of the cascades? Can we identify influencers or the lack of influencers? So these are the questions that drive our study. So before I actually talk about the modeling work, I just want to give you a brief overview of our measurement methodology and some properties that we observe about these UAGs. Okay, so here is just a brief overview of user interaction through Facebook applications. So the OSN, right, the middle box there, basically represent the OSN platforms such as Facebook, or at the beginning you have other Facebook platform, OSN platform as well, like MySpace. Now, every interaction between users actually have to go through the OSN platform. So in some sense, the OSN platform really serves as an indirection box, right? So in this case, so let's say user A wants to use a third-party application to interact with user B. You will send an item to the application server, and that request has to be routed through the OSN platform, the OSN server. And that got forwarded to the application server. So let's say, just for an example, this is a gifting application. A wants to send a gift to B. Then the application server will basically made up the response. And that response also has to be routed through the OSN server. And then it will forward it to user B, and the response is also, user A is notified by the server about the success of the request being forwarded to B. So what we did was we started collecting data at the application server. Now, there was actually a little story behind it. So what happened was in 2007, my PhD student, I recruited a new PhD student, Atif Nazir, from Pakistan. And the first thing he said to me is, well, Professor, can I spend some time develop Facebook apps? And at the time I say, sure, but I have one condition. You have to start collecting data for me, for your research. Right? Again, because I was just motivated by just curiosity about how does the OSN workload will look like. And so he started collecting data at the application server. So we anonymized the user ID for privacy concern to address privacy issue. We have timestamp of all the activities that are generated by the user. And we have specific actions, right? So we know what type of actions the user is generating. So the actions include things like installing the application or using the application to, if it is a gifting application, send a gift from a user A to user B. Or if it is a gaming application, there are some game-specific actions that we recorded as well. So since then, well, I have to say, I guess both my student and I have been pretty lucky. My student is very talented in developing applications and also maintaining the interest of users in his application. So he has, I think, developed and launched about a dozen applications, and a lot of them actually got really popular. So he actually launched two types of application. The first type is what we call social utility or gifting applications. So they are very simple. They only allow users, for example, in this case, Facebook users, to send a virtual gift or item to their friends. Okay, so that's the extent of the interaction. And then the receiver, the user B, can decide to ignore, accept, or accept the item and then install the application and turn around and send out more items to other friends. And then the other type of application he launched is gaming applications that allow not just friends, but also non-friends to interact with one another through his gaming apps. Now, as I said before, actually a lot of his applications at their peak time actually rise to the top 1% of Facebook apps. And so his applications manage to attract, order of millions, tens of millions of users. And so as a result, we actually have a huge amount of data, user activity data, to help us in our study. In fact, one of his applications, iHeart, at one point ranked the third most popular Facebook app at its peak. And we have about, during just the monthly active users, we have like 30 million users. So using this data, of course, the first study that we did was trying to understand just the global usage characteristics of the user activity graphs generated by these apps. So, the first work that we did was published in IMC 2008. But I do want to show you a few results from there that later on actually guided us in our more recent work in modeling the evolution of UAG. So at the time, we only looked at 3 weeks of data, right? So a snapshot of the UAG, the user activity graph. And as you can see, within that just that 3 weeks, we actually have a lot of user data to look at. Like the total unique users that we track within those 3 weeks are 5 million for God Love, one of the gifting application, 1 million for Hugged, and 100,000 for Fido's Club. So some of the quick results. Now, one of the things that we found out is that the user activity graph, if you look at the total number of users, and then you look at the sheer size, right, of the user population, and the clustering coefficient and the diameter of the graph, right, what jumped out is that it's actually a small network. I mean, despite the huge population size, it takes 10 or at most 45 hops, right, to reach any users in the graph. So that's the diameter of the graph. Now, the other things at the time that we looked at is we're interested in basically addressing the scalability issues. Where we know that the storage, retrieval, and processing of data would be problematic, right, if for OSN-based applications, especially if the number of the user base increases, right, exponentially. So the first question we ask is it feasible to do any kind of data segregation, right, in order to do distributed data storage of all this user-based activities or user-based information? So we look at, well, what about are all the users and how connected are they, right? So naturally, the first question is, well, if there are multiple disconnected components, then potentially we can basically do data segregation that way, right? So if the users are not interacted or connected with one another, maybe we can cluster them and separate the different group of user data. For the users that interact a lot, we can co-locate their data. So that was the original thought. So the first thing we check is how many users actually belong to the largest component, right, of the graph. And it turns out that across all the three applications that we looked at, 86 to 92% of the users actually belong to one big component in the graph. Although there are actually some other disconnected components, but they only account for a small percentage of the users. So unfortunately, that kind of a straightforward, very naive approach of trying to segregate data based on connected components of the graph doesn't quite pan out. So the next thing that we ask is, well, how about community structure? Can we actually identify a cluster of more connected nodes in this interaction graph? Basically, a more connected subgraph, right? The structure actually exists. And if it does, can we actually predict the community formation based on information we can gather, again, from the user profile, things like their geographical locations or Facebook networks that they belong to? Now, the result that we show, unfortunately, is that that question, right, to answer that question, we actually need to know the type of or the genre of applications the user are using, because you can see that if you look at the structure coefficient, right, it's very different between the gaming application, which is the Fido's Club, and social utility or gifting application like Got Loved and Hugged. Okay, so typically when the structure coefficient is greater than 0.3, we say that it has actually the graph has a strong structure, and in this case, for social utility or gifting applications, we do see a strong structure, but not for the gaming application. And so we actually also look at, well, can we actually predict, if it has a community structure, can we predict somehow, right, how these users are connected, right, how are they structured? Now we look at where the users are coming from, geographical diversity for different community that we identify. And as you can see, they are all over the place, right? So there is not really an easy way for us to cluster users based on their geographical location. Similarly, we look at Facebook network diversity, which networks they belong to. And again, especially for the gifting applications, they are all over. Right? So there's no easy way to do that. Now, one of the other things that I want you to remember from this first set of exploration is that the UAGs have very different structures depending on the dynamics of the application. So here, the gaming application exhibit very high user engagement, but not so much for the social utility application. So, for example, if you take the left graph, it was plotting, we are ranking the users based on the most number of activities generated to the least, And you can see that for Hugged, which is a gifting application, about 50% of the users contributed 80% of the activities that are logged at our application server. Whereas in Fighters Club, in the gaming application, 10% of the users actually generate 80% of the activity. Okay, so it's much more skewed. Moreover, the gaming applications typically allow non-friends to interact with through this application. So as a result, if you look at the UAGs, it loses the structure that you would have expected if the underlying friendship graphs, right, has exhibit certain amount of structure. So there is something that we would like you to keep in mind as we move to talk about our efforts in modeling these UAGs. So the results that I show you so far is based on the 3-week snapshot of a UAG, right? So it's a static snapshot of the graph. Now, obviously, the next question we ask ourselves is, well, do the graph properties that we see stay the same, or are they different? How do they evolve over time? How do OSNs go viral? What is the growth process of these UAGs? And can existing graph models that have been proven to generate acceptable synthetic friendship graphs suffice when we use that to model UAGs? And if not, how do we go about developing a new parameterized model that we can use for generating synthetic graphs? Now, why are we interested in this thought process? Well, the first usefulness of this is, well, if you can come up with a parameterized model that can be used to generate synthetic graphs that faithfully describe user interaction on the graphs, it makes it easy to share the parameters instead of the raw data, right? So we can address and kind of avoid the privacy concerns of sharing user-generated data. And then second, we also view it as one possible way of condensing information. So instead of tracking billions of activities of the logs that we collect at the application server, now if we can identify what parameters are useful to derive from those empirical data, we can just track those, and then we have a model to generate the synthetic graph given those parameters as input. So the first thing we did was, well, we went to the literature, and then we found out that there are several models that have been designed for friendship graphs. These are intent or feature-driven algorithms like nearest neighbor or forest fire that researchers have shown recently that they can generate synthetic graphs that are statistically similar to OSN friendship graphs like the one you see on Facebook. So we went ahead and tried to test those models using our data. So we want to see if those models can generate synthetic graphs that have a similar properties as the user activity graphs that we observe. And the answer is no. They are not accurate when we use that for OSN UAGs. So the left side, this graph is showing the degree distribution of our graph. This is in degree. And on the right-hand side is the out degree. So remember, the UAG graphs are directed in nature, right? So user A can send multiple gifts to the friend. So those are the out degrees from the node. And when you receive something, those are counted in the in degree. Now, the in degree distribution seems to be predicted pretty well by the existing friendship models, but not the out degree. Okay. Anyone has any guess why that could be the case? No? No one wants to try? All right, I'll move on, and we'll come back to address this, why that's the case. Now, if you remember earlier, right, from our measurement characterization of the graphs, I mentioned that the UAGs are not application agnostic. It's very sensitive to the dynamics of the application itself. So as a case study, we went back and looked at Facebook apps and see, okay, what are the different types of applications out there that are popular? So among the top 250 apps, we found that about 74% are gaming, and then the second most popular genre is gifting. Now, in order to try to model the UAG evolution path and also the growth process, we actually really need to understand what is the growth mechanisms, right, what is the growth process of the Facebook apps? Basically, how does Facebook apps recruit new users? Because when you recruit new nodes and you generate activities, that's how the UAG start to grow. So we look at Facebook apps and their growth mechanisms, and basically, we identify 4 different channels. The first is called application request, and this is the one that is used by all Facebook apps, right? So it's a basic invitation-based growth mechanism. So basically, you have a user A using the application, you send AR to a friend who might ignore or accept it, and that's how the friend found out about the application, and then you can turn around and recruit other users. Now, one thing to keep in mind, though, is up until late last year, Facebook actually imposed daily send limit on the AR that you can send out. So each user, right, each day can only send out, about 20 application requests to a friend, among all the friends. And the reason is that they want to curtail spamming or avoid spamming activities. And then the newsfeed stories, we found out that among the top 250 applications, about 88% of it actually prompt users to share newsfeed, basically personalized posts on the users' profiles about the applications they're using. And the third category is emails. About 36% of the applications ask for email addresses, so they can do targeted user recruitment for new applications that they launch. And then the last category is paid advertising. And a lot of gaming applications actually use that, right? They pay for users. So as a start, in order to try to derive a model for UAG, we look at gifting application genre. And the reason is we found that for gifting applications, it uses only one growth mechanism, AR. So it makes it much cleaner, much simpler to deal with. And so we want to know if you have applications that only uses one growth mechanism. Can we actually derive a parameterized model to model this UAG that is generated? Now, in order to study UAG evolution, obviously we need a long-term data. So we have 3 sets of data. All 3 are from gifting applications that my student launched. But only iHeart, we actually managed to collect the data since the initial launch. So, and the other 2 applications, we have about 14 months of data, but those are after the application has already matured and attracted a lot of users. So in terms of iHeart UAG, so this is showing you the profile, basically. The number of activities on the y-axis, and x-axis is the number of week, basically. So the 27th week in 2009 up until the 35th week in 2010. And so as you can see, they are very distinct. There are 3 distinct phases of the application. When it starts ramping up, becomes very popular, it's peak, and then after that is what we call the fatigue phase, when the application loses popularity. So we look at how do we go about deriving the generative models for this type of dynamic graphs, right? Dynamic networks. Now, this is an open active research area, and if you look at the literature, there are 2 classes of approach, right? So the first approach is you generate static snapshots of the graph, right, throughout different times. So it's try to discretize the graphs. And you study how the graph parameters changes through time. And the second category is you are trying to model the graph evolution as a continuous process. Right? So you want to predict each node's activity based on its current and previous states. And then by modeling the individual user's activity and interaction pattern, it will give rise to the macro level evolution of the user activity graphs. So first we'll talk about the first approach, right? So the 4 parameters that we look at, right, as a start, the graph properties of interest are in and out degree distributions, number of connected components, percentage of users in largest connected components, and clustering coefficient. Now, because we need to discretize, try to come up with snapshots of the graphs, of course, the first question is, well, how many days or weeks should we use, right, to observe and generate a snapshot? So we looked at how do all this graph properties of interest change through the observation windows, basically. So x-axis is the number of days that are in our observation window in order to generate the snapshotted graph. And then the y-axis is the graph property. So here I'm just showing the clustering coefficient. Now, so what we found out is that actually most of the graph properties of interest stabilizes after 7 days, after a week, right? Because, I mean, the users who are going to respond after they accept an invitation, they will respond within a week. If they don't respond, most likely these users that receive an invitation are never going to respond anyway, okay? So, all right, so we look at weekly snapshot on the graphs, but we are also interested in the different phase of the evolution phase of the application. So we selected 10 weeks that are sampled randomly across these 3 phases of the apps and use that empirical graph as the basis of our study. So the next thing that we try is to look at the degree distribution, right? We ask ourselves, are there simple approximation that we can do here in order to describe how the in or out degree distribution look like? So we tested several common models, common distribution, power law, exponential, stretch exponential, and log normal. And then we found out that for the in degree distribution, it can be fitted pretty well with power law. But for the out degree distribution, there are actually 2 distinct phases. I mean, as you can see, the red line is an algebraic decay, and then the black line is log normal. Okay? Now, it turns out that you might actually see also the spikes, right? The almost periodic spikes. And it turns out that those spikes are multiple of the daily sending limit. So remember I asked you a question why there is a discrepancy between the existing friendship model versus the out degree distributions that we see in our UAG. Well, one of the contributing factor is that it's not really free. Right? The sending actually costs something. The sending costs more than receiving. You can receive as many hearts, as many gifts as you want, but in terms of sending, because the OSN platform have an upper limit of how many actions, right? How many gifts you can send out per day, or how many friends you can actually contact with the applications a day, there is actually a cost associated with it. So it contributed to this very distinct feature of the out degree distribution. So we identify a few parameters that we think are important as input to this generative model. And so here are a few, actually I'll talk about 4 of them. So alpha is a percentage of new targets. So what is the probability a user will target a previously unseen user? So it's a way to recruit new users into the active population. Beta is the proportion of users that initiate no activity. So even if the node receives multiple invitations, it will never generate an activity. It will never actually install the application or use it. Active user duration is once a user starts sending or generating activity using this application, how long does it stay in the system, right? So when we model it with the power distributed with exponent gamma d. And then daily activities is how many outgoing edges does the user generate, and we approximate it with a power law distributed curve with exponent gamma m. And then daily activity limit is something that is set by OSN platform, so in this case, Facebook. And we also have number of seeding users and 0, which is the number of users appearing in the graph without being invited first by other existing users. So these parameters we can actually derive empirically from our data, from our UAGs, right? So here is just showing you the different parameters. So for example, at the peak, you can see that we have about 30 million of users, millions of activities generated, and these are some of the parameters that we derived. And M, you will notice that this is actually the limit set by Facebook, but it's not constant. And that's because Facebook actually deployed some learning algorithm, and this limit is actually varying based on the learning algorithm. Okay, so this is how our model works. So you place N0 seeding nodes. So these are nodes that appear in the graph without receiving an invitation first. And then you we divide the whole process into 7 time slots, so 7 days. So again, because we are generating weekly graph, right, snapshots of weekly graph. And in each activated node, it can add a certain number of edges into the graph according to the distribution M, which is approximated with power law with gamma M. And then out of the outgoing edges with probability alpha, you are targeting new nodes. You're recruiting new nodes into the graphs. And otherwise, the other end of the edges will be chosen among existing nodes according to preferential attachment. Okay? So basically, it means that if the existing nodes have high number of in degree, then you are more likely to attach this outgoing edge to that node. And then the new nodes become active with some probability 1 minus beta, otherwise it stays silent. Okay, so this is the ratio of inactive users to the population. And it will continue the process and stop after 7 time slots. So that's our probabilistic model for generating weekly UAG graph. And we tested it with our empirical data. Right, so the distribution, this is showing the degree distribution of empirical out degree, in degree, with the out degree and in degree from our simulation using this model. And we found that it actually matches pretty well. And we tested it not just for iHeart, but also for 2 other popular gifting applications, and we find similar match as well. All right, so we also tested out not just across the different applications, but also across different phases of the applications, right? So for iHeart, we tested it with weekly graphs from the pre-peak, peak, and post-peak. Now, what we found is that it matches pretty well in all cases, except for the one where the week that is coming from the weekly graph, where the application is at its peak, and you have a lot of users and a lot of activities. Now, there's a slightly discrepancy, and then we went back and looked at it, and we know that the out degree distribution, right? The outgoing links that we use in our model to generate, we are approximated with a power law distribution. But we also know that empirically, when we look at it, we know that it actually has 2 regions, right? It has a power law line, and then later on is a log normal. So we actually replace the power law distribution, and then we replace it with log normal, which actually require now 2 parameters instead of 1. And we found that we get a perfect fit then. If we use a more accurate distribution in generating the outgoing links. So in order to evaluate the accuracy, we look at basically 2 metrics. One is KS statistics that basically compare the distribution of the observed graph versus the distribution of the degree distribution based on the simulated or our model. And we actually showed that a 4-parameter model, in most of the cases, work pretty well. The 6-parameter model work well also, especially for the peak activity. But the rest of the time, the 4-parameter actually is suffice. Now, again, why do we care about reducing the parameters? Because for a parameterized model, there's always a trade-off, right? It means with a model selection, we want to have as few parameters as possible as input to our model. Now, so those are so for our model, we also actually show some steady-state results. We actually show that the asymptotic degree distributions of our model converge to power laws. And we also proved that our model can create synthetic graphs with more than a single connected component. So even though part of it, of our growth model is based on preferential attachment, but we actually succeeded in generating graphs that have more than a single big connected component, which is important because that's what our empirical graph actually look like. So again, as I mentioned, the utility of model is it can generate realistic UAGs from gifting apps without sharing data. And it's applicable to basically other applications as long as they use one single growth mechanism that is similar in our case, which is the AR growth mechanism. Now, obviously, there are still open questions that we continue to explore. How do we extend it, the model UAGs from gaming, another type of, or genre of applications? And how do we bridge UAGs across weeks and months? Because here we are looking at generating weekly snapshot of the graphs faithfully. But then obviously the next step will be, well, can we come up with a model that can actually describe it as the evolution of the graph as a continuous process? So that is actually something that we continue to look at, and I have some new results to share with you in terms of trying to predict macro-level evolution of UAG by modeling micro-level node behavior. So that's the second type of approach. So obviously there has also been some previous models that have been proposed to describe the continuous growth process and the evolution path of a graph. But most of the previous models actually assume nodes neither join or leave, right? It's a pretty static graph. But in our case, that's not true, because for UAG, both edges and nodes are transient. So one of the related models that is relevant to our case is the SIR model, the susceptible infected recover model. So SIR model represents a temporal graph as a dynamic process on a static network. Now we cannot directly apply it because of several reasons. So one is, in our case, the underlying contact network may not exist, right? We do not know a priori the underlying graph of the user population, right? Because of the dynamic nature of the applications, you can actually become friends after using the applications. You can recruit new users or new friends into this graph. Second is there is no state for temporary dominant or silent in the SIR model. So in the SIR model, the node can be susceptible to some infection, and it gets infected, and there's some probability of recovered, and after that, again, it becomes susceptible. Now, in our case, when we say infected, so let's say a user started to adopt the application and install the application. Now, we can send out some activity, so some virtual gift, and it can stay silent for a long time. It can be dormant for a long time, and then come back and be active again. So we find this actually, this work around SIR model very useful in the sense that it provides hints on how to characterize a temporal network. So, so the premise is that if we can actually describe the behavioral pattern of individual nodes, then it actually naturally gives rise to the evolution of the UAGs. So we went back and looked at our empirical UAGs and tried to understand the node behavior, right? So here are some observations that we found. We found that in three of the three gifting applications that we looked at in our case, more than 50% of the users are active for less than 20 weeks. Again, this is a hallmark of gifting applications in general, in the sense that the users, there are high churn of users, right? They are, as opposed to gaming applications where it's more engaging, and you actually have a core group of users playing it, the same game over and over for a long time. In the gifting application, the users can come and go. They can use it for, use it to generate gifts and then, or send gifts, and then they might go away, right? So what are the implications? Well, here in our case, nodes do not continuously infect the target node. So unlike the SIR model, so we need to actually introduce what we call a dominant state. So we look at how to model the node transition in our case, right? So we introduced 3 node states. So active means nodes that generate at least one action within a week. Alive or dormant means that it has a positive probability, but it's less than 1 probability that you will be active and generate more activities in that week. And then quit means that it no longer generate any action. So for users that decide to uninstall the application, for example. So in order to model UAG evolution, we look at a few things. So we look at what is the active ratio. And we found out that actually across time, no longer how old the application has become, the proportion of nodes that actually become active is pretty stable. So there are some, it's a constant that we can estimate. Now, what about expansion cost? We call it expansion cost. Basically, this says what is the ratio of the current number of active nodes to the number of new nodes joining. I mean, intuitively just means that how many users have to be actively generating activities in order to recruit new nodes. Now, not surprisingly, this is actually the increasing cost over time. So as the application gets mature and then gets, when the freshness factor of the application goes away, it takes more and more. Right? It takes more and more activities and active users to recruit a new user to join. And then lastly is the lifetime distribution. Once a user becomes active, right? In our case, actually, we found that a large portion of the nodes actually are only active once. They use the application once to generate activity, and then that's it. They go away. And then the remaining nodes, the lifespan can be nicely approximated by exponential distribution. So fitting all this together, we basically built a state transitional model for the nodes that represent users in our case. Now note that actually what is interesting is this is actually the transitional probability actually is time dependent. Right? There is a strong dependence on the freshness of the application. So the T prime is actually the number of weeks after a particular node joined. So the transitional probability depends on the absolute time of when the application is launched and at what point does the user actually join the application after the application is launched. It's also sensitive to the time where a particular user joined the application. So both are taken into account. So after we build this transitional model, so basically the next step is, well, we want to know if it can actually explain and give rise to the macro level evolution that we observe. So we try to use this as a predictive tool. So the question we ask is, if let's say we can extract the necessary parameters for our model based on initial measurements, say the first 20 weeks after the application of the application, can we actually forecast the active user population from then on? And the answer is pretty promising. In this case, we show that for iHeart, right? So based on the first 20 weeks of measurements to gather information that we need to build the node transitional model, we found out that we can actually predict the rest of the evolution pretty well. And then we use that to the same method to apply to two other gifting applications that we have, and we actually got pretty good result as well. We can actually predict the evolution pattern of the UAG, of the active population size for the application. So the next thing we try to do is, try to validate this by looking at other applications that are not developed by us. So we want to know, are there any, because we want to make sure that it's not sensitive to some specific properties of our own application. So we look at just a sample of gifting applications out there and data that we can get from public domain. So these are active user statistics that we get from appdata.com. And again, apply our model. We take the first 20 weeks of data for training and deriving parameters for our model, and then use our model to predict the evolution. And again, we see pretty good match. Okay, so just a brief summary. So we actually, have a continuous model that can capture node behavior, individual node transitional pattern, and then use that to predict the macro level graph evolution. The next step that we want to look at is whether or not we can capture the evolution of the structural properties. So far we are predicting just the envelope, right? So the population size. If you can find more details in our paper that's going to appear this year in conference. And if you're interested, you can shoot me an email, and I'm happy to share the preprints with you. And then the other topic that is ongoing in our group is try to quantify the influence of a node. Right? How do you differentiate the influence of multiple centers? We have some preliminary results that show that highest degree nodes are not necessarily the influencers, and there are more than one type of influence that exists in our UAGs. So there are trendsetters, users that are influenced in kind of more traditional sense of influencers because they actually generate huge cascades. But then there are also nodes that act as amplifiers. So if you look at the cascade growth or the cascades that are generated, they are kind of two hump. And the second hump is due to these amplifying nodes. And then there are nodes that are bridge nodes because they bridge multiple communities together or multiple clusters of nodes together. And again, there's a factor that contributes to a cascade growth. And then another topic that we're looking at is how does one UAG affect the growth in another UAG? So we're interested in looking at cascade across different networks. So to summarize, our group has collected and analyzed user activity data from top Facebook applications for a while. And so far, we have some success in developing a parameterized model for generating synthetic graphs, weekly graphs for UAGs. And we also have a dynamic model for UAG evolution. Using the same set of methodology and setup, we also look at a few other things in our group. In the past, one is using, since we have control to the application servers, we augment that with synthetic clients that we deployed on Planet Lab nodes and use that to reverse engineer what's happening inside Facebook as an interaction platform. So that was published in IMC 2009. And another related piece is we also look at how we can differentiate fake profiles from real profiles by learning the behavioral patterns of real users. So what we found out is that if you look at fake profiles on Facebook, they are nearly identical with the real ones if you just purely look at their friendship properties. Because fake profiles are basically generated by users or created by users, and they can advertise those fake profiles to other friends and try to make it look like a real users. So in order to differentiate them, we actually have to look at the actual activities that are generated associated with different profiles. So lastly, I just want to acknowledge my collaborators for this work. Bala Krishnamurthy from AT&T Lab Research, and another colleague, Raisa D'Souza, who is an expert on complex networks at UC Davis, and my students. Thank you.
Thank you. We have time for maybe one or two questions, if anyone would like to pose a question. Thoughts, comments? Great. If not, enjoy the rest of the afternoon. Thank you again.